Okay, in this lesson we are going to look at graphing rational expressions. So similar to polynomial equations or functions, we want to get as much information as possible before we sketch our graph. So with rational functions we will be having some vertical and horizontal asymptotes, so that's important. It might ask us to state the domain. We want to find our x and y intercepts, any extrema, so local max and min, intervals of increase and decrease, points of inflection and concavity, and then sketch our graph. So these are all the things that we want to try and find with our rational functions. So let's look at an example. So here y is given as x and x squared over x squared plus 1. I'm just going to write, okay, that's not what I want to do. Let's get rid of that. Okay, I'm going to write down the first and second derivatives. These are generally given when you have questions like this. Just saves you some work in finding them yourself. And it also makes sure that you have the correct derivative before you start finding all these properties. Because if you have the wrong derivative, you're going to get the wrong information. So often you will get, and in the guide you will see that you will have the first and second derivative already done for you. Okay, so let's have a look, things that we want to find. So let's look at our asymptotes. Okay, so our horizontal asymptote, remember that we could find the limiting value as x approaches infinity. So if we take the value of the function and we divide by the smallest or greatest degree. So I'm going to take the numerator, divide by x squared. I'll take each term in the denominator, divide by x squared. And let's see what we get. So x, that's 1 over x in the numerator. In the denominator we have 1 plus 1 over x squared. And then as x approaches infinity, any of these values that are divided by a variable are going to get really, really, really small. Like 1 divided by infinity is basically 0. So that would be 0 and that would be 0. So therefore my horizontal asymptote would be at 0. The other way to do your horizontal asymptote is to use the 3 rules we did in 4U. So in 4U we said if the degree on the bottom was bigger, it would be 0, which is in this case the degree on the bottom is bigger. If the degree is the same, it would be the leading coefficients. And if the degree in the numerator is 1 more, it would be oblique or slanted, which we're not going to use. Okay, so either method is fine. My vertical asymptote is dependent on the denominator. And we get x squared equals -1, which is not possible, so there are no vertical asymptotes. Okay, moving on. We want to, we could do the domain from here. So my domain is any real number because there are no vertical asymptotes. So we can use any value for x. I want to find my x and y intercepts. So the x-intercept is when y equals 0. So x equals 0, so 0, 0. And my y-intercept is when x is 0. And so y is also 0. So my x and y-intercept are both at 0, 0. Then I want to check my intervals of increase and decrease and any local max or min. So that's where I'm going to use my second derivative. So my second derivative is given. So when we are doing this type of question where it's a rational expression, critical numbers occur when f prime of x equals 0, which is what we were used to doing with polynomial functions, but it can also occur when f prime of x does not exist, which would be the denominator. Okay, so where f prime of x equals 0, that's going to be the numerator of the rational function. And where f prime of x does not exist, that's going to be the denominator. So those are the 2 points at which we want to check. So if I take the numerator and set it equal to 0, we get x equals plus or minus 1. If I take the denominator and set it equal to 0, I do not get an answer. So there are none here. So the denominator is not going to give me any critical numbers. So I have a possible local max and min at 1 and -1. So let's go to a new page here. We'll just continue on with this. Okay, so I've got my critical numbers at 1, -1. So I'm going to do my table to determine intervals of increase and decrease. And we'll put our factors down the side here. So we'll just pick some numbers. We get negative in the first interval. We get positive in the second interval. And then we get negative in the third interval. So it's increasing when it's less than -1, and then decreasing, then it increases between -1 and 1, and then decreases after. We have a local min at x equals -1, and we have a local max at x equals +1. So I'm just going to put those numbers here. When I substitute those values into my original function, I get, let's see, 1 would be 1/2, and -1 would be -1/2. So those are my local max and local min. So this is the min and this is the max. Okay, the next thing I want to look at is concavity, so I can get a little bit more information about what the graph looks like. So we're going to do concavity. Am I numbering these? I'm not sure. So yeah, let's call this number 6. So that's my second derivative. So the second derivative is given and again, those points of inflection could occur when f double prime of x is 0 or it does not exist, but the denominator we've already decided is not going to be a value, so we'll just do 0. So either 2x is 0 or x squared minus 3 is 0 and x is equal to plus or minus √3. Okay. So we're going to check these values into our table to determine concavity and any points of inflection. And it might be helpful to change √3 to a decimal just when we're picking values. It's easier to know what value to pick. So we're going to put in 2x, x squared minus 3, and x squared plus 1 cubed. So I'm going to pick a number less than -1.73. So that's going to be negative, positive, positive, so negative. So it's going to be concave down to there. I'll pick a number between -3 and 0, so I'll just pick -1. So that's going to be concave up, and then I'll pick a number between 0 and 1.73, so I'll just pick 1. So negative, so concave down, and then we'll pick a number in this interval. So concave up. So that gives us a bit more information when we're graphing. Okay, so at this point we should be able to put everything together. So let's just summarize here. so that because we can't see all that information, so I'm just going to summarize it here. So what do we know? We know that we have a max at 1/1/2, and we have a min at -1, -1/2. We have points of inflection. So I can see here there's a point of inflection, and here, and here. So we have points of inflection at -√3, 0, and +√3. What else do we know? We know it's, if we look at our increasing, decreasing table, we know it's, let's see, decreasing when x is less than -1 and greater than 1, and it's increasing in between. So let's start looking at this sketch. So I'm going to draw my grid. 1, 2, 3. Okay, so at, let's do it in a different color. So at 1/1/2, we have a local max. At -1, -1/2, we have a local min. At -1.73, we have a point of inflection. So that's approximately here. And that point, I subbed it into the equation, I get -4. So it's a little bit higher than this one. So approximately, I'm going to say about there. And then likewise, we had one at +1.73. And that worked out to be +4.3. So that's approximately here. And then, of course, 0, 0 was the x and y intercept, so concavity is going to change there. So before -1/2 to -0.73, it's going to be concave down. So it's going to be concave down. Then it goes concave up, and that's where it starts to increase. So I know it's decreasing to -1, and the concavity changes at -1.73. Then it's going to increase to +1, and it's going to be concave up to 0, and then it goes concave down to +1.73, and also turning at +1, and then it's going to go concave up. So that's what my graph is going to look like. You could check in Desmos if you want to type in the equation just to confirm what it looks like, but those are the information properties that you want to determine. So with a rational expression, we're adding these x and y, vertical and horizontal asymptotes, so that's going to be important. We want to find any x and y intercepts, we want to find intervals of increase and decrease, and local max and mins, and then we want to check concavity and any inflection points.